All right. What I have. This is a galvanometer. This measures. Oh, struggle. This measures small amounts of current. So the galvanometer measures small amounts of current. What does this measure?
Small amounts of current.
Okay. Now, what I have are two wires coming off of this. Is there any power supply connected to this?
No.
No. This is not battery powered. I'm not plugging this in. It's just a meter. Okay. These are just wires. Is this a complete circuit? Yes. Complete circuit. Okay. Now, if I take this wire and I shake it, nothing happens. Just shaking a wire. Okay, shake that wire. Okay. But if I take that wire and I shake it in a magnetic field, now is copper attracted at all to magnets? No. If I take this and I shake it through this magnetic field, what does this thing measure again? Small amounts of current. So if you were back in the 1800s and for whatever reason you're playing around with a wire and a magnet and you had a galvanometer, and you were the one that discovered this, and you're entrepreneurial, how could you package this? How could you sell this idea and be a quadrillionaire at this moment in time?
Generators.
Meaning what?
They generate current using magnets.
We just created electricity with wires and a magnet.
Whoa.
No power source. That is crazy. I mean, that is a game changer.
Where does it come from?
Just doing that.
That's electricity.
That creates electricity.
So you could light a light bulb with that.
You could light a light bulb. Very, very, very small light bulb.
So like one of those Christmas lights or small?
Not even.
Not even.
This measures really small amounts of current. Okay. So but the concept is there. Does that make sense? Okay. Now I can up that a little bit by connecting this to a solenoid, which is just one wire wrapped a whole lot of times, kind of like around a cardboard toilet paper tube. Okay. And I take a weak magnet. This is super strong. Okay. And I can run it through here and notice how much more current I'm producing.
So you can light a bigger light bulb.
I could still won't be able to light a light bulb, but have a better chance of it.
Better chance than nothing.
Does that make sense? Okay. Have a seat.
I was talking opposite. I'm sorry.
Okay.
I appreciate it. Okay.
I gotta.
So loud. Like, mom can hear it. Like, why are we doing so I did have
My thing was I should have stayed with it.
I was
The thing is, one guy to promote. I did that one was on there 3 times.
Oh, yeah.
All right. So by the end of this lesson, you'll be able to describe how voltage and current is created with a conductor and a magnetic field, describe how a generator works, and describe the difference between AC and DC. So, foundational fact number 1, moving charge particle creates a magnetic field. Foundational fact number 2, if a charged particle is moving through an external magnetic field, then it experiences a magnetic force. Okay. The last foundational fact in this chapter is if a conductor experiences a changing magnetic field, then voltage is induced or created across the conductor. And if this conductor is wired in a complete circuit, then current is created. Okay. So if a conductor experiences a change in magnetic field, so you just saw 2 examples of that. We had the wire and we ran it through the magnetic field of the big ram's horn magnet. Experienced a change in magnetic field. The other one was we took the magnet and we ran it through the solenoid, through the center of the wire loops. Both cases, the conductor, the wire, experienced a change in magnetic field. Therefore, voltage is induced. We had both of those conductors, those wires hooked up in a complete circuit, and we measured with the galvanometer the induced or created current. Cool that? So each foundational fact has a right-hand rule associated with it. Right-hand rule number 1, if moving charged particle creates a magnetic field. 2, if a charged particle is moving through an already existing magnetic field, experiences a force. Right-hand rule number 3, foundational fact number 3 does have a right-hand rule associated with it, but we're not going to worry about it. Okay? So let us try to figure out how this works. Okay? So what I have is, we'll start with the magnetic field. So I've got this big horseshoe magnet, North Pole, South Pole. Got a magnetic field going from north to south. I take that and I put the South Pole behind the board and the North Pole's out here. So this is creating this magnetic field. Everybody okay with that? Okay. Then I take this conductor, say a piece of copper. Okay. Is copper magnetic? No. Iron, nickel, cobalt. Those are our 3. So it does not interact at all with the magnet at this point in time. Okay. But what I'm going to do is I'm going to grab a hold of this is what? I'm going to grab a hold of this wire and pull it through with some velocity. So I'm like, in this conductor, in this piece of copper, protons and electrons. They're just living peacefully. They don't know anything. They're not causing anything. They're like, doo-doo-doo. Then all of a sudden their world is being moves like, whoa! So you have now charged particles that are now moving through an already existing magnetic field. What's going to happen when charged particles are moving through a magnetic field? Tell your neighbor what happens when charged particles are moving through a magnetic field. They experience a force. Show me which way these charged particles are experiencing a force. Text your right hand. So fingers are going in. Thumb goes to the right. Positive charged things are being forced up. Okay, so I'm going to be a realist here. They can't move. Electrons are being forced down. They can move. So electrons get forced down. Does that make sense? Do the electrons like to be in this arrangement? Like, yeah, it's electron party, woo! Like, no, it's like, this is horrible. I can't believe this. Would they be motivated to go somewhere else? Specifically, up here. Does that make sense? As we move this through here, this is inducing an electric potential difference from this side compared to this side. It's kind of like if we made a battery. Negative, positive. See the voltage across that? How these electrons are motivated? They don't like this. Do that. Okay. Do we have a little late on the draw there? We're early on the draw. Let's see, where was I going with that? If I'd stopped this, what would happen? What would happen if I stopped moving this? What would happen to the electron? What would the electrons do? There you go. This has to be experiencing a changing magnetic field. Does that make sense? Okay. Do I have a current? Not yet. I just have segregated charged particles. Good with that? But if I hook this up, what's going to happen now? The fun starts happening. Electrons like, yeah, I am out of here. Ding. What happens when electrons get back up here and we're still moving it? That makes sense? So, by definition, what is the direction of current? In the opposite way the electrons are flowing. This essentially becomes a battery. Out of positive, into negative. So we only get a current when it's hooked up to complete circuit. And this is how generators work. Crazy. Go to that. Questions there. Okay. This diagram, you're looking down on top. So it's flying this way. This is the right. This is the left wing. Tell your neighbor what you think.
Oh. At least you copped it.
It's your
And I love doing these things.
This one. Okay, that's
Okay, it's just
like the school. Same
that's what you
concept.
think. I'm trying to do that.
Yeah, actually it was.
It is now. It's a net. Oh, last year. Just make it like a bowl.
Correct answer is? Correct answer is electrons are being forced here. Left is positive. B. Go to that. There you
I understand the electrons are being forced up because of like the right hand rule, but why are they being forced up?
Because they're moving through this magnetic field.
Okay.
It's like foundational fact number 2. It just does. Yep. Yeah, that. Like, maybe a little deeper. It creates its own magnetic field because it's moving charged particles. Because they're moving. And so those two interact and it gets forced out. Trick question. Correct answer is C. Tell your neighbor why. Why is there no current? Not hooked up to complete circuit. It is moving perpendicular, but is not hooked up to complete circuit. You have an induced voltage, but there is no current. All right, now give it a shot. Tell your neighbor.
Wait. No.
No, I think you're right. It would be the same. If you
Correct answer is okay. So your hands like this. Okay. Electrons, a realist point of view. Electrons are being forced this way. Does that make sense? So Ben Franklin follower would say that protons are moving in the opposite direction the electrons are going. B. Okay. All right, with that, Mega. Yep. The whole conductor is being moved up. That's why the V of velocity is up. Okay. Good with that? All right. So let's pretend that my arm is a chunk of copper. I run it this way and it's hooked up to a circuit. So I've got current flowing. But once I'm out here and I'm outside the magnetic field, am I creating current anymore? That's what can we do? I could just make a bigger magnet. It's longer. Just make it really, and I just keep. At some point, I'm going to run out. So, what would happen if I ran the copper back the other way? Current would go the opposite way. Would that still light a light bulb? Yeah. Huh. So if I just did like this, and then this, and then this, and then this, I could stay in my magnetic field and still create electricity. But the electricity is going back and forth. Does that make sense? Okay. Now, the way we okay, so the standard, how quickly does this go back and forth? The standard, I think around the world, is 60 times a second. So I'm taking this back and forth 60 times a second, kind of like a jackhammer. This is like rough mechanically wise. Does that make sense? So an alternative to that, instead of going back and forth, this is where the watch the shadow comes in. I'm going to rotate it. I'm going to spin it. See how the shadow doesn't look any different than this? From a magnetic field point of view, this is identical to this. But this, spinning something at 60 cycles per second, easy, smooth. It's like we do it all the time. So that's what we end up doing. We spin the loops of wire rather than going back and forth. Right with that? And that's what's inside a generator. Okay. So this brings up this idea like, oh, this is crazy. Alternating current. This is current that flows back and forth, usually at 60 cycles per second. Alternating current, current that flows back and forth, usually 60 cycles a second. This is produced by generators. Versus direct current. This is current that flows in one direction. Out of positive into negative. And this is produced by batteries and solar panels. So up until this point, I've led you to believe that all current was direct current. Goes out of positive into negative. Only goes one way. Okay. Did that to keep things simple. But now you know enough that I can incorporate a distinction. Okay. Any type of electricity that's produced chemically, battery, solar panels, DC. Any type of electricity that's produced mechanically, you're moving stuff. In this class, we're going to assume that's AC. There are generators out there that have been wired specifically to make DC. Not really worried about that one. The default mode is AC. Good with that? Okay, so what do you think about this? Tell your neighbor. Correct answer is A. Where does electricity come from in our outlets? Power company. Power company have big batteries or big generators? Probably big generators. Good with that? Okay. All right, so this is a simple model of a generator. You got a magnet with a magnetic field. You have a loop of wire, and we're spinning it. And we're producing that current. Pre-cal, folk. What is that? That is a sine or a cosine wave, depending on which one you're looking at.
Oh, let's not do that.
And that, there's a lot of math wrapped up into that.
Wait, we're doing that?
Which we're not going to do.
Oh, thank God.
But know that that's the thing.
I do.
Could be a thing.
Is that a thing in AP physics?
Oh, yeah.
Good thing I think that.
Okay. Good with that? So, same idea. We've got our wire loop hooked up to our galvanometer. And so you see the different signals or which way the current's going. Good with that? All right. So, from a capitalistic point of view, we want to make more money. We want to produce more voltage. How can we do that? What can we do to our generator to produce more voltage? Okay, a couple things. Could spin it faster. We could. Okay, stronger magnets or more wire. And that's where this is coming in. You have a stronger magnetic field, longer wire, more loops of wire. This is length, or you can make it move faster, spin it faster. Increasing any of those is going to cause that to go up. That's the equal sign. Good? All right, come on back here. Again.
No.
Oh, I just about dropped my. There's one thing I had.
All right. What I have here is a hand crank generator. Okay. Okay. So, what are these? Magnets. What do you think is inside, in between the uprights? Loops of wire, causing them to spin. Why is the bulb flickering? Okay, I'm not spinning it very fast, but I'm also producing what? Alternating current. So when the electrons are shifting, changing direction, they're going kind of slow. It's like ooh, ooh, ooh. So it's like chuk, 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 chuk. Does that make sense? But if I spin it at 60 cycles a second, let's pretend I was a machine, you couldn't tell that that was pulsating. You all right with that? Okay. So my next question is, in an actual generator, who or what spins the wheel? There's like this big hamster wheel. I mean, we've got thousands of hamsters. Okay. So I heard some comments. One was wind. Go up to Bruxton. The windmills. Each one of those in there has one of these. Bigger, much bigger. Okay. Have you noticed that they relatively spin about the same speed? Okay, regardless of how windy it is. Their blades, their props can change their angle because what they want to do is spin this at 60 cycles a second. Cool with that? They don't. Okay, great question. So, it's geared down, just like when you pedal on your bicycle. One rotation of your pedals does not mean one rotation of your back wheel. Like one rotation of your pedals spins like 5 or 6 times. So they have the same idea in a windmill. So it's going like that, and they gear it down. So it's like 60 cycles a second. Okay, good question. Other ways we make the wheel spin, loops of wire spin. Steam is probably the most popular way. I'm going to get to that here momentarily. Give me another example. Water. Hydroelectric. So they build a dam and produces the depth of the water determines pressure. They make this really deep spot, and then they send the high pressure water through turbines, which are like propellers that spin the loop, generates electricity. Okay. So steam is by far the most popular. Okay. And how we get water into steam, we do what? Heat it up. How do we heat it up? Okay. Most popular is we burn stuff. Coal, We're kind of transitioning away from that, but we still have natural gas. Burning that. My father-in-law used to work in power generation. He said that burning stuff is like 85-90% of the power plants using like the electricity that we use in America. 90% of that is produced by burning power plants. Windmills can't touch it. Windmills is a nice idea, but it does not produce. We're going to see a lot more solar farms up north as well. The technology is getting better, but it's not there yet in terms of like shutting down power plants.
Very hard.
I'm not going to say never. Not in my lifetime, not in your lifetime. But here's the other thing. Like, oh, it's clean. Well, what happens if you throw those solar panels into the landfill? So it's like when you think of clean, you got to think of the whole life cycle of stuff. Like, I'm all about researching ways to make things cleaner. Okay? My personal opinion, nuclear is the most sustainable. So the nuclear reaction gives off heat, and we use that heat to boil water and send the steam through turbines. The downside with nuclear is if something goes bad, it really goes bad. It's more just like nuclear fallout, like some boom, but like that makes that area like it's not good.
Things that happen to Chernobyl and Fukushima are like really free acts.
Right. Right. It like I would say that's the way to go. Yes.
So what happens to an electric car?
The battery goes in the landfill.
Is that worse for the environment? Depends on how much you drive.
So trash in a car, it's just metal. You can recycle a lot of that. You're burning fossil fuels to like gasoline. You're literally burning fossil fuels in the engine itself. An electric car, you're burning fossil fuels to produce electricity, and then you have the battery on top of that in the landfill. I think it's a little better, but not as better as people want to think they're being better. So, you do that. Have a seat.
I just know rated at 7, the maximum severity on the nuclear events.
Sorry.
I didn't know that. The other one is 7.
No. This morning.
Okay. Last question. Tell your neighbor what you think.
Yes, it is.
Gel. I have a gel at work.
Actually, no, yesterday.
Is that when you came?
No, I
What's your
asked her
second
in. My aunt. So let's go
favorite?
next time. It's like
We were like, we're looking at Chernobyl because we didn't know anything. I just knew that like this is radioactive.
But I also did.
Correct answer is?
I don't know.
Correct answer is A. Just energy. When you plug something in, when you plug something into an outlet, all you're doing is making the electrons in the wire move back and forth 60 times a second because it's alternating. This is what makes things light up. This is what powers things. Just the electrons jiggling back and forth. Okay, good with that? Got a worksheet due on Friday.